Thanks very much, Lars. Yeah, thanks for inviting me here for what's turning out to be a very productive time and asking me to speak. I'm plugged in? Good. Yeah, so as Lars said, my usual gig is doing quantum gravity, string theory, and things like that. So over the last 20 years, when I give a colloquium, I'm usually faced with the challenges of taking very esoteric stuff that I barely understand and nobody really understands, and trying to convince people that A, there's something interesting going on here, and B, that they can understand something from it. And this is a totally different topic, one where the goals really are to convince you that the physics here is simple enough that we should really all understand the basics of physics and energy and climate to the point that we can articulately communicate with our students and people about it, and that we can be involved in what's a really important issue of the time. Let me just start with a quick anecdote. So a colleague of mine told me this story that when his son was maybe 3 or 4, he built a little yellow blob out of Legos and brought it to his dad, and his dad said, "Oh, this is really cool. What is it?" And the kid said, "Chicken." And the dad said, "Oh, bok, 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 bok." And the kid said, his son said, "No, silly. Not the animal chicken, the food chicken." And he obviously hadn't quite made that connection that the word chicken was not applying to two different things, but just different ways of using the same thing. And I mention this because I feel like a lot of students, when they, undergraduates and some of us even at more advanced stages of doing physics, have a hard time thinking of the energy that we work with in physics, where you have a conserved quantity, which governs kinetic and potential energy. Students go to a mechanics class, they learn about that quantity, and then they go get in their car and they drive off to Target. And the idea that the gas they're using, which they also think of as energy, is somehow the same thing, I think takes a while for people to click on when they study physics. So part of the idea, I think, is we want to be able to bring together the energy as we use it as society and the energy as we think about it as scientists. So let me just sort of run through that quickly as kind of a prologue, and then we'll talk a bit about the physics of energy and climate and what we might have to say about that. So energy, of course, is a really central concept in physics. When you take your first physics course, you learn about a harmonic oscillator. You've got kinetic energy. You've got potential energy. The energy sloshes back and forth between them. And basically, one of the neat things about energy is if you take any physical system and try to understand the flow of energy in that system, you pretty much understand the important features of that system for most physical systems. So you take a circuit and the energy sloshes back and forth between the inductor and the capacitor. It gets dissipated in the resistor, and understanding that really is a big part of understanding many physical systems. In quantum mechanics, of course, energy plays an even more fundamental role as the Hamiltonian, the thing that governs the time evolution of the system. But basically, as physicists, when we look at a system, we want to understand the flow of energy. And the planet is no different. There's an open source Earth model called the Energy Exascale Earth System Model, developed by LLNL. You can download the software and do your own little climate analysis. But this allows people to understand the flow of energy in Earth considered as a system as a whole. The solar energy comes in, heats the oceans and the atmospheres, it moves around, gets re-radiated into space. And you can ask questions about climate, about warming, about sea level rise and things like that based on these simple models of how energy flows, or complicated models in this case, models of how energy flows in a physical system. So this is physics in, energy in physics, in science. At the same time, our technologies for harnessing energy have really been the key that has driven the development of society. Back to the very early days where the first technology of fire is basically a way of releasing stored up energy for light, for heat, for cooking. Moving a little further on to agriculture, that's basically the most fundamental form that we need energy in, is fuel for our bodies to run. Harnessing agriculture is a way of harnessing an important energy system. And then, of course, moving further into the modern era, the Industrial Revolution, the steam engine revolutionized transport and industry. Going a little further, we learned how to transmit electrical energy, a great efficient way of getting energy out to lots of people. Internal combustion engine, petroleum. Southern California wouldn't be what it is today without those developments. And at some level, all these different energy harnessing technologies are really ways of taking energy that originated in the sun, was perhaps stored for years or millions of years in systems, either biological systems or fossil fuel systems, and then re-released. And in the current day, we're learning to more directly tap into that solar energy. So this is great. So we've developed this great society based on our ability to harness energy systems, and that's all good. The tricky thing, of course, is that our use of energy, all those beautiful technologies we just talked about, has led to one of the central challenges of the 21st century, which is the impact of that energy use on the world around us. I mean, we'll talk more about this, but temperatures are going up. Seas are rising, more extreme weather events. I don't have to tell you in California about the fire season, which is definitely being affected by changes in climate, ocean acidification. These are all global issues with Earth systems that are affected by the way we're using energy. So we have to come to grips with that. So in this context, about 10 years ago, as Lars mentioned, Bob Jaffe and I started teaching a course at MIT. The course is aimed at undergraduates in all majors, and the idea was basically to introduce students who had a freshman physics background to all the ideas that they need to understand pretty much all of energy systems, all the sources, convergence, storage, uses, and side effects like radiation and climate change. So this was one key goal. Another goal was to use energy as a theme to unify the understanding of modern physics. And as I said earlier, if you understand the energy in almost any physics system, you understand a lot of the physics of that system. And so in some ways, energy provides a great lens to introduce students who are not physics students to a lot of important aspects of modern physics, quantum physics, thermodynamics, nuclear physics, all these things. If you're focused on the energy questions, you can teach a lot with that focus. So last year, after about 10 years of work, we finally got out this very thick textbook, which Lars and others can use as a paperweight. So one thing I want to emphasize is that, again, neither Bob nor I really have specialized in our research on energy-related things, but we do think that this is a really important topic, and it should be included in many ways in the physics curricula. So the messages I want to convey with this colloquium are, first of all, that, as we all, I think, understand, physical science actually lies at the core of real-world energy systems and problems. And I think that as physical scientists, it really behooves us all to understand energy systems, at least at a basic level, so that we can communicate intelligently about them. I'll have a few examples of physical scientists who make statements that maybe are not quite right, and I think we should all know enough that we don't make really wrong statements, because it doesn't really help. And I think we should educate others. Again, we should bring this into the classroom, and even in your mechanics class or your E&M class, we can bring in examples from real-world energy problems, thermodynamics obviously, that are relevant to these things, and I'll say more about that. So I do think that most of the challenge right now to solve these problems is largely a political, social, and economic challenge. Obviously, there's a lot of room for technical innovation, and I think there are people in this room, we were just talking before the colloquium, who are working on technical innovations in energy storage and transformations, and that's obviously a really important thing to work on. But the right decisions have to be made, and they should be informed by sound science, and we should help be the people that communicate what the sound science is. There was a Stephen Colbert episode early this year in which there had just been this discussion of this panel that Happer was going to run on energy and climate. And Colbert said, does it make any sense to have a physicist run a climate panel? That's like having a professor of English literature, a doctor of English literature doing my annual physical. And I want to say, no, that is not correct. Physicists are exactly the right people. You just have to get the right physicists. So that's part of it. So what I want to do in much of the rest of this talk is run through the role that physics plays in some issues of energy and climate, walk through the situation with regard to climate. Many of you know a lot about this, but I think it's helpful to sort of go through carefully what we understand, what's based on simple physics, and where there's a little bit of complexity and uncertainties. Talk a bit about energy systems, how we might solve some of these problems, and then I'll say a few things about energy in the physics curriculum. Let's see. Okay, so let's talk a little bit about energy and climate. So if you look at the use of energy, and we'll go back, of course, by energy use, I mean second law of thermodynamics, just degrading energy to a less useful form. In the colloquial sense, when we burn gas, we're using energy. The rate at which we use energy as a society has approximately tripled in the last 50 years, and it's kind of enlightening, I think, to deconstruct that. If you look at the last 50 years since like 1969, the per capita energy use has gone up by a factor of about 1.5, and the population has approximately doubled. And if you multiply 2 by 1.5, you get 3. So the energy use has gone up by a factor of 3. So we currently use energy at a constant rate of about 18 terawatts. 18 times 10 to the 12th joules per second. Per capita energy use is about a gigajoule a day. That's about 5 times the global average. And it's helpful, I think, to compare that to the amount of energy there is in the food you eat each day. If you have a 2,500 calorie diet, you eat about 10 megajoules a day. So each person is using about, yes, Dave?
Well, not to correct your numbers, but
yeah.
You said from 1960, it looks like a factor of 3.5 in population.
So it's roughly a factor of 3 over a 50-year period. Let's say it was maybe 160 here. I think it's 160 to 500. Oh, sorry. Sorry. This is over. The claim is that this happened over 50 years. So the 50 years starts here. 50 years starts around 48 or 50 and goes up to about 75. That's about 1.5. Population around here is 3.5 up to 7, about approximately doubled. So the dark lines are just where I have better data. It's not the starting of the 50 years. 50 years starts in 1969, which is about here, around 3.5. Maybe it's a bad graphic, but basically there are 2 different data sources I took it from, and this is an approximation. This is hard data, or harder data. And so the beginning of the 50 years is about there. It's pretty close to a factor of 2.
But this 18 terawatt, how to compare with kind of total budget of energy, like for the sun or whatever?
Sure, we'll get there. On a later slide, we'll see 173,000 terawatts from the sun. It's 1 part in 10 to the 4th of the solar energy that hits the planet. And we'll talk about that. Yeah, that's exactly the right question to ask. Right. So, but we use this amount. So one way to think about this is that it's like each person in our US society has about 100 servants working for us full-time every day, in the sense that we are using the energy that it takes to fuel about 100 people. So all your washing machines and cars are using up about 100 people's worth of energy. Okay, so where do we get it? Roughly 85% of our energy comes from fossil fuels. This is 1984 numbers, sorry, 2014 numbers. Things haven't changed too much. There is gradually a bit more renewables coming online, but this number has only changed by a few percent over the last 10 years. So most of this comes from oil, coal, and natural gas. And you can ask, why is that? Well, there's a number of reasons. Fossil fuels are very abundant. They're a very compact source of energy. We have a very well-developed infrastructure and technology for extracting coal and oil, natural gas. And there are enough resources right now for about 200 years at the current use rate. If you allow for interconversions like converting solid fuels to liquid fuels, you can, for instance, at times when nations like Germany or South Africa didn't have access to petroleum or liquid fuels, they would just do a conversion through the Fischer-Tropsch mechanism. It's not very efficient, but we have enough resources that we could run on fossil fuels for 200 years or so. And there are definitely some pollution issues like car exhaust, mercury mine tailings, but one can argue that these might be relatively manageable with technology and that they're somewhat localized. With better emissions controls and better controls on your coal plants, those aren't crazy bad. The biggest issue, of course, is the greenhouse gases, the CO2 and methane emissions that are affecting the climate. Okay, so there's a lot of really beautiful and simple physics in understanding roughly what's happening in the climate system. So I want to sort of walk through that. Again, many of you are very knowledgeable about this, but I think it's helpful to just step through some of the main facts so we have a good understanding of that. And again, these are all great examples of using. When I say that the physics of most of this is simple, I mean if someone who has taken an undergraduate physics curriculum should be able to understand most of the basic physics of climate and energy systems. So, one way of thinking about the climate, the simple number is just the mean temperature of the surface of the Earth. It's a good proxy for climate. And this is regulated by a nice and familiar piece of physics, radiative balance. Basically, in radiative equilibrium, the power coming in is equal to the power going out. So you asked about what's the total amount of energy. Total energy coming from the sun, we take the insolation at the top of the atmosphere, which is about 1366 watts per meter squared. We multiply it by pi r squared, the cross-sectional area, and we get 173,000 terawatts. And we'll come back to the fact that this is just 10 to the 4th times bigger than the amount we're actually using. It's a useful thing to think about. But just for now, let's talk about climate. So about 16% of that is reflected by the surface. So the surface albedo is 0.16. And so we can do a very simple physics model to estimate the equilibrium temperature of the Earth. We can assume, for example, that the atmosphere just consists of oxygen and nitrogen, that there's a homogeneous temperature, and that the Earth radiates as a black body. And we use the Stefan-Boltzmann Law to get the power out. Sigma T to the 4th times the area is equal to the power in. We solve for the temperature using our knowledge of this constant, and we get about -6 degrees Celsius. So it's a very simple calculation. You just need to know a little bit of basic physics. And it's reasonably close, but it's too cold. Actual current surface temperature is about 14 degrees Celsius. So we want to do a little better than that. So the thing, of course, that makes the difference is the greenhouse effect. The reason it's not 20 degrees colder or so Celsius is because molecules in the atmosphere, primarily water, but also CO2, absorb and then re-radiate outgoing thermal radiation. So we solve this equation, sigma T to the 4th A, as if there was no clouds, moisture, or CO2 in the atmosphere. When we put in an atmosphere, it changes the equation. So now you can do a slightly more sophisticated, but still very simple model where you have a single layer of atmosphere. It will absorb all the outgoing infrared radiation at some particular level and then re-radiate it up and down. The incoming light energy will be, more of it will be reflected. The actual albedo of the Earth, as measured by experiment, is about 0.3, including clouds and other atmospheric phenomena. We repeat the calculation, and we get about 30 degrees Celsius. So now we're a little too high. But again, we've made simplifications. The real system is a bit more complicated, but it basically has these features. We have this 340 is that 1366 divided by 4 because the cross-sectional area is pi r squared, whereas the total area is 4 pi r squared. So we get 340 coming in. Some of it gets reflected, about that 30%. Infrared radiation goes out. Some of it actually passes right through the atmosphere and the clouds and the water vapor and the CO2, depending on the frequency. Some of it gets re-radiated up and down. And then there's convection and other things that make this all height dependent. So again, this is a system that is relatively well understood in terms of the energy balance. And the actual answer is that the surface temperatures average to about 14 degrees Celsius right now. Yes?
Yeah, I have a question. So the amount of energy that the sun transmits to Earth is not a constant, right? There is a cycle of solar activity.
Yes.
So these fluctuations of solar activity in terms of energy, are they larger or smaller than the human energy production? So if you look at fluctuations.
Good. They're probably on the order of human energy production. There's production, but they're much smaller than the added radiative flux from the CO2 we're putting in the atmosphere. Right? The reason the planet is getting warmer is not because of our using of energy. It's because we're putting CO2 in the atmosphere, which is increasing the greenhouse effect. It's increasing the net downward radiative flux from the atmosphere. And that amount is much larger than the changes in the solar constant by a factor of 10 or so. Yeah, and we have actually the exact numbers in the book. There's a whole discussion of that. I don't remember the exact numbers, but I'm quite confident that there's an order of magnitude difference between the changes in the solar fluctuations and the downward flux.
But you mentioned that the solar energy is 4 orders of magnitude larger than what humans produce, right? So if there is even a 1% or less.
Absolutely. Absolutely. So I'm going to come back to this. There's a point later in the talk where I will mention the role of solar fluctuations. where you can get a pretty good estimate of what the fluctuations are. And let's return to that question at that point. I'll try to remember to say something more about that, because that actually reflects the long-term changes in temperature, which we'll talk about in a few minutes. Okay, so this is the current atmosphere, and what's happening right now is that the atmosphere is changing. As we use all those fossil fuels and burn the carbon, CO2 levels are going up, so this is the famous Keeling curve measured in Hawaii, where you get the number of parts per million of CO2, and this has gone up from the pre-industrial 280. We're now over 400. And there's a yearly fluctuation as the northern forests, where there's more vegetation, suck in a lot of CO2 in the spring and then release it in the fall. So how does that affect radiative balance? So again, this is physics which is pretty well understood. You can measure the absorption spectrum of CO2. So this is from the online HITRAN database. You can actually download the numbers yourself for the frequency-dependent absorption. Notice that this is logarithmic in the vertical axis. And given the current atmospheric configuration, you can do a calculation, which is if we double the amount of CO2, what is the net radiative forcing in the downward direction? And that amount is roughly 3.7 watts per meter squared. The radiative forcing refers to the downward flux at the tropopause. And so I'm trying to remember the number for the scale of the variation of the solar fluctuations. I think it's a couple of watts per meter squared, but it's slightly smaller than that, but it goes up and down. We'll talk about that more in a minute. So this is, again, a direct calculation. You simply take the CO2 absorption spectrum, you take the current atmospheric configuration, and you ask what happens if we double the amount of CO2. And in order to offset that forcing, you just plug in your Stefan-Boltzmann radiation law, you get a delta in temperature, and the direct effect is that it takes about a 1 degree Celsius change in temperature to offset this. So this just shifts sigma t to the fourth to match the forcing. So this has been understood since Arrhenius, like 100 years ago. There's no question that if you put more CO2 into the atmosphere, it gets absorbed. The direct effect is that the temperature goes up. And if the only thing that were happening were the CO2, doubling CO2 would lead to a 1.2 degrees Celsius rise. The tricky thing is there are lots of feedbacks. And this is where, so everything up to this point is completely solidly understood, and I think that no serious scientist could sort of look at this and really disagree substantially with anything I've said. Once you start bringing in feedbacks, it becomes a more complicated process. So an example of a feedback is ice albedo. As the temperature goes up, polar ice melts. That decreases the reflectivity of the northern part of the northern hemisphere, especially near the pole. As the ice melts, that amounts to more downward radiative forcing. So that is a positive feedback, where the more warming you get, the more forcing you're going to get. And the climate is a very complicated nonlinear system. You can do a linear analysis where you basically take a downward forcing, you change the temperature, that gives the backward forcing that balances that. That gives rise to some feedback parameterized by lambda, and then that gives rise to an additional forcing, where the forcing F1 is lambda times the change in temperature. That then has to be offset by another delta T1, and you sum them all up and you get one of our favorite formulae geometric series. And so we see that the net change in temperature is given by -1 over the original feedback parameter. This is the thing we essentially already calculated, where if we get 3.7 watts per meter squared of forcing, we get 1.2 degrees of temperature rise. That has to be multiplied by basically lambda naught over 1 times lambda naught over lambda naught plus lambda to get the actual answer in a linear analysis. Notice that this formula has the property that if lambda comes close to, if for instance lambda naught is -3.2, if this number approaches 3.2, this goes to infinity and the linear analysis will diverge. That's a kind of a runaway feedback. Okay, so this is where it gets complicated, and lots of people, including people here, work on global climate simulations. So there are these so-called general circulation models. This is a summary from the 2 IPCC reports, the IPCC Assessment Report 4, which was 2007, and the Report 5, which was 2014. The numbers in red and blue, which are the means of all these climate. This is taken from about 20 different simulations. These are the different feedbacks. I mentioned ice albedo, so this is actually a fairly small positive feedback. The biggest feedback is water vapor feedback. Basically, as it gets warmer, more water goes into the atmosphere, and as we mentioned, water is the biggest greenhouse gas, so that causes more downward radiative forcing, so that's a big feedback. On the other hand, the rate at which the water vapor density changes as you go up, called the lapse rate, is also affected, and that's actually a negative feedback because it tends to equilibrate the temperature, so you radiate up higher at a higher temperature. So that offsets that a bit. So often people combine those into the water vapor plus lapse rate. And then there are clouds. Notice that clouds are the most poorly understood thing. This is one of the biggest challenges in climate modeling, is really nailing down clouds. And there's lots of people working on that. There's a lot of uncertainty in the clouds. So the upshot of all this is that based on these very detailed climate models, which are still lacking certain things, as clouds, there's a lot of uncertainty, ocean thermal energy transport, there are a lot of questions about in terms of reproducing paleoclimate, but this is our best scientific understanding, and putting these numbers together, the estimate that you get, that the IPCC gave, which comes from these different climate models, is that the change in temperature, if we double carbon dioxide, is expected to be about 3.2 degrees Celsius plus or minus 1.3. So it's important to notice this big uncertainty there. And one of the things which I think it's very hard to communicate to non-scientists is how to treat uncertainty and risk. And this is one of the biggest challenges for society. You know, if doubling the CO2 gives 3.2 plus or minus 1.3, does that mean we don't worry about it because it might only be 1.9, or does it mean we should really worry because, like when you put your seatbelt on when you get in your car, it might be 4.5? And that's where different people have different takes on how to read that. Okay. Now let's look at the temperature data. So this is the estimated global surface temperature since about 1850, taken from 3 different sources. There's some controversy on exactly how to take these numbers, but these are quite solid, I would say. There are large local variations. Biggest effect is at northern latitudes. Something you sometimes hear people say is, oh, they looked at the temperature data and it doesn't look like it's warming. And often that's because people looked at it in about 2010. There was an apparent hiatus for about 10 years here. And so when we started teaching this course, actually, this is a little difficult to explain to the students because if you just looked at the last 10 years, it looked pretty flat. But in the last 10 years, it's been just shooting up. So this now just looks like a little bit of noise. And there's lots of people that have different explanations for why there was a little hiatus, but it's moving up very quickly now in the last 10 years. It's perhaps instructive to think of this in a longer-term context. If we look at the last 2,000 years, and here you have to use more proxy data, things like tree rings and other things like that. So this is a little less solid, but it's still pretty solid, our understanding of these numbers. The temperature exceeds by a long shot what we believe the temperature has been over the last 2,000 years. And in fact, it exceeds what we think the temperature on the planet has been for several million years. As I'll mention later, 60 million years ago, it was actually a lot warmer, and we'll come back to that. But in the last couple million years, it's been pretty cold. It's been colder. The last 2,000 years, it's looked, like this. And we clearly have this sort of hockey stick thing sticking up. Now, there's a little bit of controversy about what's going on in this period. Basically, up to 1950, I think it's fair to say that part of this change since 1950, the first part of it, the first half degree, was in part a recovery from the so-called Little Ice Age. So the Little Ice Age was driven by a combination of different solar activity levels and volcanism. And so if you look at the effects of those two things, it's on the same order of magnitude as what we've seen so far in temperature change, but it's a little bit smaller. And while basically solar activity levels can explain, if you look at the yearly fluctuations in solar activity levels, they can explain if you assume the climate sensitivity parameter that we just calculated or just described, they can explain about 0.5 degree of change in temperature, but they can't explain a lot more than that. And same with volcanism. So it is believed that volcanism and changes in solar radiation led to this Little Ice Age, a dip where it got colder for a few hundred years. Part of what was happening up to 1950 was recovery from that, but everything at this extra 0.5 to 1 degree rise since 1950 can really only be reasonably attributed to anthropogenic effects in particular the greenhouse gases that we've been putting out. Current CO2 levels are 410 parts per million. If you plug that number into the climate sensitivity that we just talked about, that would give, by the IPCC sigma estimate, about a 1.6 degree temperature rise. So that's a temperature rise that we've only seen a part of. The full impact of the CO2 we're putting in the atmosphere, because it's a slow system to respond, will take 100, 200 years to rise to the temperature that even our emissions so far will produce. So we may have seen 0.5, 0.7, maybe 0.8 of a degree of rise so far, but that's probably only half of what we'll see from what we've already put in the atmosphere. So people, just coming back to your point again, people who argue that solar fluctuations have a larger role to play, the only way that could be the case, since we know what the changes in solar fluctuations are, the only way that could be the case is if the sensitivity parameter was larger. And if the sensitivity parameter is larger, it would mean actually that the impact of the CO2 would be even worse. So if you compare radiative forcings, the radiative forcing from the CO2 that we're emitting is significantly larger than what you would see from the, you got a whole bunch of questions. Mark? Okay.
The 3.2 degrees per doubling, is that doubling relative to pre-industrial levels or doubling?
Yes, doubling relative to pre-industrial levels. So if we got up to 560, the prediction is the temperature would go up 3.2 degrees from where it was in pre-industrial times if we hit 560 parts per million.
So another 1.6 from where it is today.
Correct. Yeah. Okay, great.
I have a question.
Yeah, Mark.
What are the error bars on that earlier data, like before 1600?
Yeah, they are larger. I don't have them here. They're larger, but they're not a degree. They're, and I think there is some controversy about exactly how big those error bars are, but I think there's a general consensus that these are pretty good numbers. And we'll come back and look at actually a longer term. There's a lot of different proxies you can use for temperature. This is like based on tree rings and other things. If you want to go further back, you have to use like cores and variations in isotope levels and things like that. And there's a whole story there. Yeah, question?
So there was this boundary minimum in the Second Law of Thermodynamics. There were no sunspots on the sun.
Yes, exactly. That's like right around here.
So is this the right proxy to determine the solar kind of energy output, the magnetic activity?
Yeah, so there is a correlation between the rate of sunspots and the total output. And you can measure that. I mean, in recent decades, we have been able to measure that very precisely. And that leads to like up to a watt and a half per meter squared of change in total insolation, I believe. But it's less than 3.7. Okay. So this is what's going on. Let me change gears a little bit, and I have a few statements that have been made by physicists. So this is a little bit of a quiz regarding climate, and I'm going to take a poll and see who thinks these statements are correct or not. So the first statement is one that Freeman Dyson and many others have made. The statement is, radiative forcing grows logarithmically with CO2 levels. How many people think that statement is correct? How many people think that statement is incorrect? Okay, I'm glad I brought this up. The statement is actually correct. So the statement is that the radiative forcing, not the delta temperature, but radiative forcing grows logarithmically with CO2 levels. And what that means is that if we double the CO2 and we get 3.7 watts per meter squared, then if we quadruple the CO2, we'll get 7.4 watts per meter squared. So this is actually correct, and it's implicit in this notation of F2x. And the reason for that can be seen in the absorption spectrum of CO2. Remember I mentioned that this is a logarithmic axis. So this thing is actually dropping exponentially. So what happens when you have CO2 in the atmosphere is there's a window in which all the frequencies are absorbed, and then there's a little window where some of the stuff is absorbed, and then nothing is absorbed outside that. So what happens when you put more CO2 in the atmosphere? It basically moves the absorption wavelength out a bit. But since this is an exponentially dropping curve, what that means is that in order to move out the same amount twice, you have to double the amount of CO2 each time. So it's actually correct that the forcing is logarithmic. And so in the linear regime, at least, the change in temperature will be the change in temperature times the log base 2 of the mass of CO2 over the initial mass of CO2. Of course, there are nonlinearities. You can push yourself beyond thresholds where all kinds of unusual nonlinear things can happen. But this statement as made is correct. And again, I think it's important to understand which statements people make are correct and which aren't, because some of them have ramifications, and if you don't know which ones are correct, then you can confuse a lot of people, and then people can also use that against you if you make incorrect statements, obviously.
But there is no kind of critical thresholds or whatever, because the regime could be changing.
Absolutely. This is very nonlinear, and there are definitely thresholds where some things are going to change, and we don't understand those very well. Those are not modeled in the linear response. They're not modeled necessarily very well in the climate, and I'll talk more about a few of those things. Here's another statement. Stephen Hawking made a statement at one point that human action could push the Earth over the brink to become like Venus with a temperature of 250 degrees, again, alluding to that 1 over lambda naught minus lambda. How many people think that that's a correct statement?
What time scale?
I think he's implying in the coming couple hundred years.
Okay, that makes somewhat of a difference.
How many people would say that's a correct statement? How many people would say that's probably an incorrect statement? Right. So Stephen Hawking was an amazing physicist, and I have incredible respect for his work on relativity and black holes and things, but this statement is actually not right. Anthropogenic climate change and warming are going to cause huge problems and devastation and lots of human problems and lots of ecological problems. But it seems like this doomsday scenario is pretty much impossible. And there's two simple things I would point at. One is this logarithmic effect I mentioned, that if we double the amount of CO2, we get a logarithmic response in the forcing. The second one is, and I mentioned this earlier, we can run through paleoclimate data going back 60 million years. And this is roughly what the temperature profiles look like. Again, the error bars are much bigger here, and we're not as confident about how to read the proxies. But because we found fossils on the regions that were at the poles, we know that there was no ice at the polar caps millions of years ago. We know that there were forests flourishing on the poles. 55 million years ago, it seems that the amount of CO2 was probably 5 to 10 times higher than it is now. And the temperature was probably 5 to 10 degrees higher. Sea levels were hundreds of feet higher than they are now. It was a totally different planet. Life flourished. That's when mammals evolved at the end of this Eocene optimum. It's unlikely we're going to go anywhere near that regime. And in order to realize this doomsday scenario here, we would need to go presumably beyond that regime because the Earth tolerated this quite well. Yes?
Are those high temperatures somehow related to the event that made, got all the dinosaurs extinct?
No. The dinosaur extinction was, it is believed, caused by some combination of the meteor impact in the Yucatan and volcanism. That was not, I think, did not contribute significantly to this. A lot of this actually is driven by what's called tectonic scale changes, which has to do with changes of where the Earth's land masses are. Changes in, you get, for instance, when India hit Eurasia and formed the Himalayas, it made these big mountains. That caused a lot more chemical weathering, which sucked CO2 out of the atmosphere. That's one of several mechanisms that has driven very long-term tectonic scale CO2 changes in the atmosphere. And then things like the formation of the southern circumpolar gyre, which keeps the South Pole from, we have a big landmass on the northern pole, a smaller landmass, not a landmass on the, a big landmass on the southern pole, but then an ocean around it. All these things that have to do with the placement of the climates, the placement of the continents, and chemical weathering and things play a role in those. In the recent years, what's happened is it's gotten colder. Antarctica glaciated around here. And now, in the last couple million years, climate has been driven by these Milankovitch cycles, where you get changes, periodic changes in the angle of Earth's tilt and the precession of the equinox. And those are the things that have driven the Ice Age cycle and the interglacials over the last 600,000, couple million years. Yeah?
So do we understand where this extra CO2, or what was the reason for this being 5 to 10 times higher 60 million years ago?
Well, I think you might ask, where did it all go? And one of the pieces of that is this, one of the hypotheses for where the CO2 went is that because of the Himalayan mountain system, there's been a lot of chemical weathering which has gradually taken that CO2 out of the atmosphere. It's gone up and down over Earth's history. There were periods of time when there was very little CO2 in the atmosphere and we had what's called a snowball Earth, where basically everything was covered with ice all around. And the only way we broke out of that was there were periods of volcanism in which lots of carbon dioxide was released to the atmosphere, which again warmed the planet. So it's believed that the Earth has gone up and down through fairly high extremes of large CO2, low CO2 levels over the billions of years of its existence. But as humans, we're not really so concerned about what happened 60 million years ago. Okay. Here's another statement. William Happer, CO2 is actually a benefit to the Earth. How many people think that's a correct statement?
Versus no CO2?
Okay.
Definitely a benefit.
I think he meant added CO2. How many people disagree with that? Okay, so I would say this is true in some senses, but it's totally irrelevant to the current situation. It is true, you know, he would say, for instance, CO2 is not a pollutant. I think it's probably correct that we maybe shouldn't characterize CO2 as a pollutant in the sense that it's not toxic. More CO2 enhances plant growth in some areas. Actually, out of the 10 gigatons of carbon that we emit every year, a quarter of that gets absorbed in terrestrial biomass. It's true that warmer climate leads to additional arable land. And if we could gradually increase the CO2 levels over 1 million years, that might actually not be a bad thing. We might stave off the next ice age.
There's additional arable land. That's taken into account sea rise.
Yeah. I think, like, you know, Canada does, you know, areas in the northern part of Russia, Canada, et cetera, you get additional land opened up. Yeah. Sea level rise affects a lot of human population centers. People don't live as much in those areas, but I think the net arable land, it certainly gives new arable land. Some of it is taken away by sea level rise. Okay, but the point I want to make is this is totally the wrong time scale. That the anthropic warming is going to occur over a couple hundred years. And the CO2 pulse will be absorbed, as we best understand it, in thousands of years into the ocean. So we'll just drop back to where we were 5,000 years from now. And so these things here, while true, are not very relevant. The ecosystems, which are already very pressed without even dealing with climate change, you know, there was a report in the spring which said that 25% of species are in danger of extinction in the coming years. So these ecosystems, which are already pressed, will not be able to adapt because the timescale for adaptation is millions of years. It's not 200 years. And that'll lead to increased extinction rates. Millions or billions of people will be displaced or affected. The sea level rise is predominantly going to affect people living near the sea, which is where a lot of people live. I mean, there's a reason that we live, that KITP is situated right by the ocean. And extreme weather, drought, fires, etc. And the other thing is that there are all these unknowns in the system. There are a lot of things like the ocean sink, which is 2.5 gigatons a year right now, that may stop or reverse. If you look at paleoclimate data, when it gets warmer in interglacials, the CO2 levels have gone up. It is believed as a secondary effect of that warming, not as a driving effect of that warming. So it may be that the ocean sink will turn around at some point. This is poorly understood. Okay, so that was kind of just to make the point that as physicists, understanding something about this and not making really wrong statements or making statements that are correct and relevant, I think is really valuable for our field and for people as a whole. Okay, so how bad will it get? It's very...
For Canada and Russia becoming...
What's that?
The time scale for...
David wants to buy real estate in Russia.
Yeah, well, I mean...
It's not 1,000 years.
No, that's happening right now. I mean, species are moving northward. You know, Russia is, you know, looking to exploit resources in the polar region. Actually, the area which is most affected is the Arctic. If you look at the rate of... I don't think I have a graphic of that, but if you look at the rate of sea cover loss, that's the place on the planet that is the most affected. If you look at the delta in temperature, the polar region is the place which is going to have the biggest delta in temperature, you know, 3 to 5 degrees, much sooner than when the equatorial regions just have 1 or 2 degrees of temperature change. And that's already happening. They're predicting an ice-free, technically ice-free Arctic, which means something like 85% ice-free by like 2030 or something. I mean, that's happening very fast. If you can go online and look at the graphics of how the how the ice levels in the Arctic are dropping, and it changes almost on a year-by-year basis. It's and glacial melt. So let me just repeat that with the current amount of CO2 in the atmosphere, we're already committed, according to the IPCC numbers, to something like 1.5, 1.6 degrees of warming, plus or minus point something. So when people talk about limiting us to 1.5 degrees, that would be really hard to do. We would pretty much have to stop emitting CO2 now and get rid of all the methane production and things like that. So without a major change of direction immediately, it's going to be really hard to avoid at least 2 degrees. Again, let me just sort of bring back in a little bit of physics on some of these things. One interesting thing to look at is sea level rise. Half, at least, of the sea level rise so far is just from thermal expansion. Another nice simple piece of physics, the change in volume is just a coefficient alpha v times the volume times delta t. You plug in your number for alpha v, and you see that the mixed layer in the ocean, which is about 200 meters deep on average, raising the temperature there by 1 degree Celsius would give a sea level rise of about 4.25 centimeters. And you get more from the deep ocean and ice melt. The original IPCC prediction was something like 1 meter in a century. Now it's moving up towards 2 meters in a century, but there's a lot of uncertainty there. Another nice bit of physics, actually, which my colleague at MIT, Kerry Emanuel, works on is hurricanes. Hurricanes are essentially Carnot engines. You can look at what happens to the packet of moist air moving through a hurricane, and basically it undergoes essentially isothermal expansion as it rushes into the core, adiabatic expansion as it ascends, approximately isothermal compression, and then adiabatic compression, and then dumps a bunch of energy. And you can look at, it's powered by the disequilibrium between the surface of the ocean and the atmosphere, and as the temperatures go up, you get more energy. You just can look at the rate of dissipation of energy, which goes as V cubed, look at the rate of power going in, which is like EV, and there's a delta T there, and then see that the higher the temperature, the more energy is going to be going into the hurricanes. Again, there's a lot of uncertainties beyond the simple temperature range. The ice melt is something which is very hard to model. Current estimates are that there's going to be another meter of sea level rise from Greenland and Antarctica, but these are highly uncertain. Weather intensity, there's a study last year that drought and flooding are both likely to increase in California. Lots of species, as I mentioned, are under threat. Looking back at this whole thing 3,000 years from now, the biggest impact that we may perceive from climate change is the huge number of species which will be driven extinct by the combination of other human activities and climate change. Okay, so that's kind of I've been talking a lot about the climate system. I want to spend a few minutes talking about, more generally, energy systems, sources, uses, and where we can get the energy from. So, as a physicist, one nice thing to do is to take our energy sources and organize them according to total power and power per square meter to get kind of an order of magnitude picture of what we're dealing with. So here I've organized these. The colors indicate where the original source of energy comes from. So this is solar energy, which we said is 173,000 terawatts in total. That energy then goes into ocean thermal energy. It goes into biomass. It goes into wind. Wind and ocean thermal energy then go into hydropower, marine current, wave energy. There's a separate flow of energy from radioactivity and early thermal energy in the Earth's core, which gives geothermal flow. And then there's tidal energy, which comes from gravitational energy, which is dissipated as tidal current. So the point of organizing things this way is, first, we sort of see how the energy flows. And second of all, the things on the right here have very high energy density. So those are cheap places to find energy with high density. Wave power is good for that. Hydropower is excellent for that. The diagonals are essentially representing resources of a certain dimensionality. Everything here is essentially a two-dimensional resource that's dissipated across the Earth's surface. As the energy resource gets concentrated to lower dimensionality, the power, the product of the power per square meter and the area of that resource gives the total power. So the area measured in terrestrial lengths gives you roughly the dimensionality. So wave power is essentially a one-dimensional resource. The waves hit the coast, which is essentially a one-dimensional object. So the things to the right are economically favorable, but if we want a lot of energy, you have to go up high here. So solar, ocean thermal, wind, biomass, respectively, are the things which put us in the more than 10 terawatt range. So if you want to get all of our energy use, which is about 18 terawatts, you're going to have to get it from some of the things above that number there, above that line. So let's talk about the solar energy, coming back to your question about energy flow. So solar energy, we have about 173,000 terawatts. So 1 part in 10 to the 4th of the incident solar energy can provide all our needs. And so just looking at the energy, if we just took existing solar thermal and photovoltaic technology and deployed it on 1 to 2% of the Earth's deserts, we would get, at current efficiency is about 4 terawatts, which is enough to provide all current electric power and land transport if we electrified all our vehicles. So it's easy to see this as an order of magnitude estimate. Deserts are about 4.5% of the Earth's surface. If we take 1.5% of those deserts, that gives us 6 to 7 times what we need of our 10 to the minus 4 here. So at about a 2 to 3% conversion efficiency, we get about 30% of the 18 terawatts, or about 4 terawatts.
Are you assuming an average power?
Average. Okay. That's just average power.
But average, not peak power.
That's average.
Yeah.
I'm averaging it at, yeah, this is taking the average power density, doing all that calculation. But of course, the challenge is storage, as we were talking about earlier. So the point of this slide is the energy is there, the power is there. We just take 2% of the world's deserts, put existing technology on there, and we have the energy we need for electric power plus land transport, and we can use solar energy for heating and things like that. It's really, we're not missing the energy source. The challenge is economics, implementing it, and storage. Transmission is not so bad. You can have a 2,000 kilometer transmission line with only about 7% losses. So storage is definitely a technical problem, and then the main obstacles to this transformation, as I said before, are economic, political, and social. Let's just talk briefly about the challenge of storage. What does it take to store a gigawatt day, which is 9 times 10 to the 13th joules? And the main point I want to make here is that basic physics and materials constraints limit the energy density. Nobody's going to start a company and every 10 years come up with, or even any number of years, come up with a new battery which is 10 times more dense, and then another 10 years, 10 times more dense. It's just not going to happen because each of these approaches has its sort of natural physical limit. Mechanics is actually one of the main ways that people store energy. Pumped hydropower is the main grid-connected source of energy storage, and you're just using good old E equals mgh. If you take h as 300 meters, and you would need a mass of 3 times 10 to the 10, I think that's kilograms, which would be a volume 3 times 10 to the 7th cubic meters of water to store that 9 times 10 to the 13th joules. So it's a lot of water, but it's doable, and there are hydropower systems that do that. There's one in England that they use, and they need to use it particularly when they have commercial breaks on, at least they used to when they had commercial breaks on British television, because everybody would make tea at the same time with their electric teapots. I'm not sure if that's outdated by streaming, but it's a nice story. Okay, so let's say we try to use electromagnetism. We try to use capacitors. Well, there's a limited voltage that you can put in a volume of air. If it's just air, you can get at most 40 joules per meters cubed before you get a breakdown. If you use supercapacitors, you can get up to about 100 megajoules per meter cubed. So again, for this amount of energy, you would need 3 times 10 to the 7th cubic meters of supercapacitor. You can use batteries. These are limited by the binding energy to mass ratio of the constituents, which by just basic physics and electrochemical constraints can't go much beyond what we use in current batteries. Hydrogen fuel cells, for instance, can get us to 140 megajoules per kilogram. So again, if we wanted to store that amount of energy, we would need something like 1 million car batteries with 100 megajoules each, or 600,000 kilograms of hydrogen. Again, these are all big numbers, but they're not unmanageable. It's just a big engineering project. There are lots of viable scenarios, but they require big systems. Diurnal storage you can get, for instance, from solar thermal. It's particularly in Spain. They have a lot of solar plants where they use a liquid salt to store the thermal energy, and they can store it for a couple days in a well-insulated tank. So for day-to-day storage, that's fine. But if you really want to go seasonally, that's a big challenge. Let me just come back to the next thing going down on that list, which is ocean thermal energy. Remember I had this plot of the different energy sources. The next thing down is ocean thermal. So you might think you could get a lot from that. And that's another nice little physics lesson. In the tropics, the top 200 meters of the ocean are at about 20 degrees warmer than the ocean abyss at 1,000 meters, which is about 5 degrees Celsius. You can compute the energy content, and you get lots of energy. If you look at the amount that's absorbed in the equatorial 40%, it's a rate of about 4,000 terawatts, and you can match that to the rate at which thermal energy is transported towards the poles by the oceans. So that's a big amount, but the problem is the Carnot efficiency, if you're only going 20 degrees, is only about 7%. And real ocean thermal energy systems, they have these little things that float around, try to extract the thermal energy. It's really hard to get more than about 2%. There's a very low what's called exergy, the useful energy there. So there's lots of energy there, but it's really hard to extract. Solar energy is much more plausible because it comes at 6,000 degrees, basically. Okay, I'm kind of running short on time, so let me just say that there's a whole set of nice stories that one can tell in physics. You can talk about the second law of thermodynamics, relate it to information entropy, and use that to explain how you use up a conserved quantity, explain the lost energy from car engines and power plants. Physicists don't tend to use this concept exergy. I commend it to you. It's a useful way of describing things. We sort of skip through that. We can talk about tidal power. Bottom line is there's not enough to get much of 18 terawatts, but it's a beautiful physics story about how the Earth loses its angular momentum to the moon. Wind power is a really interesting story. If I had more time, I'd talk more about that. There's a wide range of estimates on how much wind power we can actually extract. Some people say 100 terawatts. I think those are missing the fact that you can't put wind turbines infinitely placed along the plane because there's a finite atmospheric depth. It's probably in the realm of a few terawatts. One is probably an underestimate. But it's very high quality energy, it's economically viable, and it's going to play a really useful role. And it's an open question what fraction of our 4 or 18 terawatts we can get from that. You might say, why not just remove the carbon? And then there's another nice story having to do with entropy. Basically, there's randomness in a system when you mix two different kinds of molecules together. So to separate them, you need to reduce the entropy. And you can just do a little calculation. Again, using information theory, it's like a log of 1 over c times kb times the number of molecules. So the separation requires a certain amount of energy. You do the calculation, you discover that to capture and store 37 gigatons of CO2 at 100 atmospheres would take 27 exajoules, which is more than 40% of current electricity production. So atmospheric capture and storage at high pressure takes a lot of energy. It's better to do it in a coal plant before, you do it with the flue gases, or do it before you put it in the atmosphere. Okay, you can, sure.
What about the artificial leaf idea that Nocera has developed?
Absolutely.
You don't need to separate it, that artificial leaf.
So there are various, real leaves do it as well. You can grow a forest and you pull a lot of CO2 out of the atmosphere. Then you need to sequester that. And that's certainly a way of getting energy out of the atmosphere. Any of those systems, I believe, require a large amount of surface area and a lot of time. And it's certainly a way you can do it. And you can do it with natural systems in a way that doesn't require much. But it does use up land.
The natural system just end up, again, using oxygen at night. The natural leaf. But the artificial one
Right.
is 10 times more efficient.
Yeah, I think it's a very promising direction of research. I think there are a lot of interesting ideas people have. But all I'm saying here is there's a very basic physics constraint, which is it takes a certain amount of energy to do that. If you're using solar energy, that's great. And I think a lot of these, like the actual leaf uses solar energy to absorb the carbon. I think it's a very important thing for people to study. I'm not saying it's not a way to go. I'm just saying it's hard. I'm saying there's a physics constraint that says that whatever you set up, it's going to take a certain amount of energy to do it. 2 more minutes? Okay. There are lots of other interesting limits that we can talk about that come from physics. There's the Betz limit on wind, the Shockley-Queisser limit on photovoltaics, bounds on concentrator efficiency. But let me spend my last 2 minutes coming back to this question of teaching some of this stuff in our classes. So, one of the questions that I went into this whole learning about this, teaching the class, writing the book with was, first of all, I wanted to understand climate and energy systems better, and also obviously to understand a little bit about how I can do something which might be vaguely relevant to this. And so that the broader question is, what should be the role of, what can be the roles of physicists in physics departments regarding energy? At a very basic level, it's unlikely that we're going to find a brand new source of energy. We kind of know where the energy is. I kind of outlined for you the natural systems that have the energy. I don't think anybody's going to find a brand new one. I haven't really talked about nuclear. That's a whole other story which would require more time. Similarly, it's unlikely we're going to find a way around the second law or other really fundamental constraints of physics. There are lots of opportunities, as I said, for applied physics research and energy technologies, storage, solid-state materials for photovoltaics, nuclear power. But I think that one role that all of us as physicists can play is in, again, understanding this stuff and educating students and our colleagues and journalists and politicians about what the actual facts of the science are. For the students, I think it's an important arena in which to educate students, not just from physics, but from all disciplines. And I think it actually is a net plus for physics departments because it makes the physics obviously relevant. We've had lots of students come through our class who, after taking the class, they say, wow, I didn't realize how central physics was to understanding all these important things. I want to take more physics classes. Because they didn't quite make that connection. So I think it's important that we try to include energy in the curriculum. It engages students, as I just said, with contemporary issues, makes them want to pursue further study. It, I think, clarifies the relevance of abstract material. You take this very vague stuff about entropy and the second law, you can make it really concrete and really tie it to important day-to-day physics stuff. Again, I think it helps to unify the field of physics. I found it very exciting learning this stuff and teaching it because it all came together through the lens of energy. I understand physics much better than I did 10 years ago because I tried to follow all the little threads that started with energy. And it also connects physics to other disciplines. I didn't say too much about this, but when I say physics, I really mean physical science. And that includes earth science, it includes chemistry, and lots of other things which traditionally are not at the core of physics. But I think they're things that need to be brought in to understand this. And I think that's an important direction for physics departments to connect to. So anyway, I think putting problems from applied energy systems into our basic courses is a useful thing. I'd encourage you to do that. So I'll just repeat my basic messages. That physical science lies at the core of real-world energy systems and problems. I think that we as physical scientists should understand those systems and educate others. And I think, obviously, advocacy for further research and understanding on climate and energy issues is also essential because there's not enough study being done as to even what the actual facts of the system are. Okay, I'm not here to sell books, but I will just tell you that the publisher agreed that if you want to read the book, you can use this code to get 20% off at Cambridge University Press. And the book's only $80, so it's going to be online, so okay, that's great.
David.
Yes.
Did you discuss in the book other ways of reducing the temperature, like putting mirrors in space or aerosols?
A little bit. Geoengineering. Yeah, we talk a little bit about some of those things. We could, if you have a specific question, I'm happy to talk about some of those. But yeah, those are certainly alternatives. One of the biggest issues about those things is, number one, you have to keep doing it. It doesn't really change the carbon content of the atmosphere. Number two, it doesn't deal with things like ocean acidification. Which is, causing huge problems with coral reefs and things like that. I suspect that people will start doing some of that at some point, but it would be better if we could solve the problem in other ways.
Okay. What you mentioned, the figure of 5 centimeters on the sea level rise.
Right, that was just from raising the top 200 meters of the ocean 1 degree Celsius. That's just a simple back-of-the-envelope calculation where we use the thermal expansion coefficient of water. Correct.
Which would mean by this, you have to raise the temperature by 25 centigrade.
Okay, so I had more information on the slide, and I'll just go back to it. Where was it? Yeah, so I commented there that there's going to be more rise from the deep ocean and ice melt. So basically, the top 200 meters is not the only part that warms up. There's this sort of conveyor belt. I mentioned 4,000 terawatts of thermal energy being brought northward and southward away from the equator towards the poles. As that approaches the poles, some of it evaporates, and some of that water then becomes more saline and sinks into the lower ocean. So there's a very gradual mixing over which that thermal energy, just like the CO2, is gradually mixed into the deep ocean. So then the warmer water is down in the deep ocean. That causes thermal expansion of the entire ocean. So this is just a tiny piece of the ocean. This is really just, again, a back-of-the-envelope calculation to give you a sense of how much rise we get. If you look at this graph, since 1880, the total sea level rise has been about 25 centimeters, 20 to 25 centimeters, so 4 or 5 times that. And that's already because there's some of this mixing going on, and also there's some coming from ice melt. The 1 meter that they talked about in the 2007, in the 4th IPCC report was, I think, mostly from thermal expansion, including thermal expansion of the deep ocean, and partly from ice melt. And it's now believed that a whole additional meter or 2 in the next century will probably come from ice melt. And that's not going to stop anytime soon. That's going to keep going for centuries. And in particular, there's a lot of open questions about the rate of ice melt in Greenland and Antarctica, and they keep finding that things are happening faster than they expect. Greenland is melting faster than people expect. Glaciers are melting faster than people expect. And there are a lot of open questions about Antarctica, where you get these, big ice sheets and ice shelves that if things melt close to the water, they don't really understand the way that ice behaves at those temperature and pressure regimes well enough to calculate the deformation properties to predict how fast that's going to move. And they're finding that some of those ice sheets move faster than expected. So they've upped the estimate on the amount of sea level rise from melting water, and that will probably dominate in the 200 to 300 year time frame.
See, just elaborating on that, one hears much bigger figures for the sea level rise from melting ice from Greenland and Antarctica, on the order of many tens of meters.
Certainly not in the next 100 years. Sometimes you hear numbers like, over a longer period of time, as I mentioned, back in the Eocene, we had 100 meters higher.
Yeah, so the question is sort of what timescales and what uncertainty.
Yeah. So the way I understand the current estimates, it is the next 100 years we would see somewhere between tops 3 to 4 meters of sea level rise, maybe in the next 100 years. What's that?
KITP still out of the ocean.
Right. It is a slow process, but it will be an inexorable process. As long as the CO2 is there. There's another nice back of the envelope calculation you can do, which is if you take an extra, few watts per meter squared and use that to melt ice, how long does it take to melt the ice in Antarctica? And it takes thousands of years to melt all the ice in Antarctica using a fraction of the incoming energy. So, Antarctica is not going to melt completely. That would take on the order of thousands to 10,000s of years.
Okay, so on that note, let's thank Wati.
Thanks again, Lars.